Hey everyone, in this video I'm going to go through questions 37 through 42 of the USNCO 2025 local exam. You can follow along with both the exam and the solutions document I've written in the description below. So let's start off with question 37. This question is asking what the average oxidation state of iron in halotropite is, and that's going to be our Fe over here. So there's a couple of key things to note for oxidation states. So overall, uncharged molecules are going to have an oxidation state of 0, since essentially oxidation state is kind of bookkeeping electrons in a way, and since we have a neutral molecule, we're not going to have any oxidation state. So this overall thing is going to have an oxidation state of 0, and we can break it down further from here. So, like I said, neutral molecules are going to have oxidation states of 0, and H2O is neutral, it's uncharged. So we can essentially ignore this 22H2O since it's going to contribute 22 times 0 in terms of the oxidation state, which of course is 0. Another thing to note is that ions are always going to have an oxidation state that's equal to the charge of the ion. So from polyatomic ions, sulfate has a -2 charge, so it's going to have, or 2- charge, so it's going to have -2 as its oxidation state. And for aluminum, it's always going to be +3. So yeah, now essentially we have all the information we need to start solving. So if we say that the oxidation of state of iron in this is X, then essentially we can say X plus 2 times the oxidation state of aluminum, which is +3, plus 4 times the oxidation state of sulfate, which is -2, is equal to 0. And then from there, it's just basic algebra, and it gets us our answer B, +2. Okay, let's move on to question 38. So question 38 is testing how we can identify half reactions at the anode during electrolysis. In this case, it's going to be talking about aqueous sodium iodide. So there's a couple of key acronyms that we can use to solve most electrochem problems, at least relating to the USNCO, and that's going to be AN-OX, red cat, and oil rig. So AN-OX, red cat, I've heard many different variations of this, but this is personally how I remember it. It's saying that at the anode, oxidation occurs, and at the cathode, reduction occurs. And then oil rig is saying oxidation is loss, reduction is gain. So oxidation would mean a loss of electrons, and a reduction would mean a gain of electrons. So looking at the problem here, we have the half reaction at the anode. So using our acronym, that's going to be oxidation. And using our acronym further, we're going to have a loss of electrons. So we can immediately just cross out anything that doesn't involve a loss of electrons, namely A and B. So we've narrowed down our answer choices to C and D. And essentially from here, what we can figure out is which is more favorable or more likely to happen. And there's a couple of different ways you can do this. First, you can memorize a reduction or oxidation potential of like common reactions, but you would have to memorize that pretty in depth. So there's other ways to solve it. Essentially, we're looking for a more favorable reaction, so we can discuss which is more likely to happen. So let's break it down here. C is forming an II bond, and the other non-bonding stuff is relatively negligible in terms of the energy. And for D, you have a breaking of 4 OH bonds, and 1 O double bond is formed. So essentially, if you think about which would require more energy compared to the amount of release of energy, you can immediately see that C is likely going to be our answer. So it's generally going to be more favorable, and we're going to select C as our answer. And there's another rule that you can typically apply to these problems. So typically halides, or negatively charged halogens, will form uncharged halogens at the anode Otherwise, oxygen gas is going to be formed. So that applies to most cases. So you can see here, this is a halide, I minus, and it's turning into the uncharged iodine, and that's going to be the half reaction at the anode because it's halogen. On the other hand, for other reactions, you're actually going to see D as the answer, and I won't get into why that is. It just comes down to reduction and oxidation potentials, which reactions are favorable, etc. Alright, let's move on to question 39. So question 39 is testing what changes will decrease the cell potential, so kind of your general understanding of cell potential and such. So one thing we want to do first is read over the options and see immediately what really makes sense. So decreasing the concentration of Fe2+, we definitely have to look into that a bit more. That's pretty plausible. On the other hand, increasing the size of the silver electrode, you can immediately tell it's a solid, so that's probably not going to be our answer, but let's go through it a bit. So the first thing we can do is write out the Nernst equation because it's asking about the cell potential. So a big hint is whenever you see cell potential or voltage or something on this section, you're probably going to want to see if the Nernst equation is applicable here. So this is the Nernst equation. And in this case, Q is going to be the concentration of Fe3+ over the concentration of Fe2+ times Ag+, or rather divided. Oops. So that's going to be our Q. So when we decrease the concentration of Fe2+, that's in our denominator here, so it's actually going to increase the value of Q, which is going to increase the value of ln Q. However, in the Nernst equation, this is subtracted, so it's actually going to decrease the value of E, or the cell potential, so I is going to be correct. And like I mentioned earlier, you want to omit solids from Q expressions, pure solids and pure liquids. And silver in this case is a pure solid, so you'll notice that I didn't include that in the Q, and that's the reason why II is not going to be true, since changing the amount of silver isn't really going to do anything. It's not in our equation, so II is going to be false, and the answer is going to be A. Okay, let's move on to question 40. So question 40 is testing electroplating. It's asking what's going to deposit on the cathode for a certain amount of solution that's a certain concentration in copper nitrate and silver nitrate. It's being electrolyzed with a current of 0.7 amperes for 350 seconds. So the first key equation that we need to use for this is Q equals I times T. Or in other words, charge equals current times time. And we can see that I is going to be in amperes. The current is 0.7 amperes, and then our time is going to be 350 seconds, and we're going to leave that in seconds. So our Q, or charge, is going to be 0.7 times 350, which is 245, and that's going to be coulombs. And from there, another equation that we use is N equals Q over F, where F is going to be our Faraday's constant. And I've done the computation here. Faraday's constant is this, and we have our Coulomb value from here. So we're going to get this number of moles of electrons. So what that actually means is that that amount of moles of electrons can be deposited, essentially. Through stoichiometry, we're going to figure out how that relates to silver and copper. So one thing that we need to know right before we hop into this problem is that this reduction, Ag plus E minus, goes to solid silver, is going to have a greater reduction potential than the reduction of copper. And again, there's a couple of ways you can know that. You can either just have the reduction potentials memorized, or you can know that silver is typically unreactive, so it's going to have a greater reduction potential since it's going to want to trend towards solid silver because that's going to be more stable. So since it has a greater reduction potential, it's going to be deposited first. So this reaction is going to happen before this reaction starts happening. So immediately we can already rule out B and D since in order for copper to form, silver must be formed. And you might be confused why I ruled out D if that's the case since both are forming. But keep in mind this is like our max amount of electrons that can be deposited. So it's like if this amount of copper is going to be deposited, then that means that copper would have been formed first, which is not true. So let's note it down between these two. And what we're going to do here is figure out the moles of Ag plus that we have, because you'll notice these are in a 1-to-1 ratio. So then from there we can figure out if the silver is going to be fully deposited, or in other words, if this first reaction is going to go until completion, because if it's not, our answer is A. If it is, then our answer is C. So we're just going to do some stoichiometry here to figure that out. I've done it here below. We just use the values that we have from the problem. 180 milliliters, the molarity here, and then of course we know there's 1 mole of Ag plus per mole of AgNO3. So doing that computation, we get this. And like I said earlier, because there's more moles of Ag plus than there are moles of electrons, and these combine in a 1-to-1 ratio, essentially we're only going to see 2.54 times 10 to the negative 3 moles of Ag plus deposited. So there's an excess, I don't know how that line happened, but there's an excess of Ag plus. So our answer is going to be A, since we're not going to have enough moles of electrons to start the depositing of solid copper. Okay, let's move on to question 41. So let's first identify our half reactions and kind of break down the problem a bit. So it's asking us for the standard potential of a fuel cell where methanol is oxidized to CO2 and oxygen is reduced to water. So right off the bat, we want to identify what's being oxidized, what's being reduced. Methanol is oxidized, and that is this reaction here. Oxygen is being reduced. Again, we can use oil rig and ox red cat, particularly anox red cat, because methanol is being oxidized, so that's going to be the anode here. So this is our anode. Oxygen is being reduced, so that's our cathode. And from here, we just use a key equation for electrochem, which is E cell equals E cathode minus E anode. That's just like one of the first equations you learned in electrochem. So we have 1.23 minus negative 0.02, which is 1.25. So our answer is D. And you may be wondering if you've done a couple of chemistry mocks or USNCO mocks, or you just seen like tricky problems in the past relating to like that seem very similar to this. Particularly on the 2024 local exam, there was a problem, I believe, that required you to use delta G for this for a similar type of problem. Instead of E cell equals E anode, or E cathode minus E anode. And the reason for that is that some past problems have used only one electrode and have combined two half reactions into one reaction and asked you to find the standard potential of a cell like that, which is not like actually a fuel cell because that's going to require two electrodes. So when you see like this type of like two electrodes and a reaction that's not combined, you're going to know that you can actually just use this equation here. So I recommend looking at the 2024 USNCO local exam mock and see, I think it was also like question 41 or perhaps 42. Look at that and examine the differences between that and this question 41. But for now, our answer is D. Okay, now question 42. This is a decently hard question, and it requires you to use a lot of different concepts, and it's a pretty long question. So some of the past questions throughout questions 1 through 41 you could complete in less than 2 minutes. So you're going to want to probably use some of that extra time here to be able to answer this, unless of course you're really fast. So let's break down the problem here. I'm not going to read it out loud. I'm sure you guys can do that as well. But you can see here we have a reduction of the oxo anion. So that's going to be a gain of E- electrons because of oil rig. Reduction is gain of electrons. And we can break down this question more to try to write a general reaction. We can see that we have an increase of 1 pH unit. It's like saying that there's the half cell potential is becoming more negative by this amount, but we don't need to worry about that for now. We just need to worry about this 1 pH unit thing. And again, it asks how many protons and electrons are involved in the half reaction. So essentially we've figured out that there's an oxo anion. It's being reduced, it's gaining electrons, and it's gaining protons because protons are H+, the same thing, because we can see an increase in pH units. And this is kind of misleading since pH is negative log H+. So remember that an increase in pH is actually a decrease in H+. And of course we have this hint here. So we figured out this general reaction. Essentially we have an oxo anion, the substance being reduced, and then we have a certain amount of H+ and electrons added, and then it's becoming this reduced form. So that's our general reaction here. And like I said earlier, whenever you see potential, you always want to know if you always want to see if the Nernst equation is possible. So the Nernst equation is E equals this minus RT NF, or in this case is going to be NEF, and it's actually lnq. So you might be wondering how I went from lnq to log q, and essentially all we're doing is computing this RT term, and we're going to be converting log base E of q to log base 10 of q, and you're going to see why soon. But this is also a pretty well-known equation. You might want to memorize it just to save some time, but of course you don't need to. So this is going to be our form for our reaction. Again, that's just RT and then the conversion to log q. And in this case, Q is going to be this expression. We have reduction on the product side, and then we have H+ and the substance being oxo anion on the left side. So our Q is just going to be like that, and we exclude this E- in the Q. So let's move on. We can see from here, using log rules, remember that we have log Q here. So log Q is going to equal log of the concentration of this over concentration of the oxo anion over the concentration of H+. And that's going to actually be to the power of NH, since we don't know how many moles we have. So I've used NH as a constant here. And using log rules, you might know that the log of A over B is the log of A minus the log of B. So we can rewrite this according to this. And we want to make sure to bring down the power here. So yeah, we get this for the log Q expression. And notice that this is going to be constant, because if you notice here, only H+ is actually going to be changing, because the problem says like we have an increase in pH units. Nothing else is really being changed. So we know that this is the only non-constant term. So we can rewrite it as this. And you might be wondering, how do I actually get there? Well, it's because we're immediately hinted that this is kind of like a slope type problem, since the oxo anion potential is becoming more negative by this amount for each increase in pH. So whenever you have like slope or something, you want to focus on your x or your non-constant thing. In this case, that's going to be this. And log H plus is, of course, negative pH, and that cancels out with this negative here. So we get NH times pH. Now this is great. We got back to pH, which is the problem, right? That's one of the parts of the problem. So from here, what we can do is plug in NH pH for log Q here. And you might be wondering, oh, where'd this constant go? It still is part of the equation, and you're absolutely right. But what we do is, since we're focusing on the slope, we just name a new formal standard potential. You don't need to worry about that too much, of course. If you're taking this test, you don't need to notate it like that. But yeah, we're just ignoring the constant for now, grouping it in with this constant. You notice how we changed the notation here. So now we have this final thing for the cell potential, or the half cell potential, yeah. So from here, we know that we have the slope of negative 0.118 v. So using like y equals mx plus b, you can generally see that if this is E and x is pH, m, our slope, is going to be negative 0.05916 nh over ne, and b is just going to be our constant cell potential thing. So we have this as the slope, and we know this, I'm going to write it down here for space, that's equivalent to negative 0.118. So what we know is if we divide both sides by negative 0.05916, we're going to end up getting NH over NE equals 2. And you can do the math yourself to verify that. So we're looking for a 2-to-1 ratio of protons to electrons. If we go back up to the answer choices, we can see this is the only answer that has that. If there were like 4 protons, 2 electrons, that could work as well, but there's not. So our answer is going to be C. And yeah, that's the conclusion to a pretty long but satisfying problem.